In this video, I'll derive the infoNCE loss with L2 normalized representation, which is widely used in many papers. So the goal equation that we want to derive is L contrastive encoder and temperature, and this number of samples. And this is the expectation value, where X and X position, the tuple, is from the probability distribution of P pulse, and negative samples are IID, and also this is from the P data. And you can say minus, and here's the expectation value of Fx dot Fx position divided by tau, the temperature, plus the summation of the negative samples. Same term with the first one, the exponential of Fx dot F negative sample divided by tau. And we can write here the expectation of, this transpose is to be here, tau, like this. So this is the goal equation that we want to derive, and the P positive that gets to input is distribution over Rn by n, and the P data is a distribution over Rn, and R is the dimension of this X variable. Okay, so to derive this equation, we'll go through NCE loss first, and then we'll move on to the infoNCE loss, the original term, not the L2 normalized form, but the general form. And with this infoNCE, we'll also see the mutual information maximization and the meaning of decay of divergency. And finally, we'll get the infoNCE with L2 normalized representation. Okay, so let's start. The NCE stands for Noise Contrastive Estimation. And this is the way to estimate the parameters in the statistical model. And this tries to do the logistic regression to tell apart the target data from the noise. Okay, so let's say X is a target data and X tilde is noise sample. Then we can say this target X is from the target distribution, where the theta is parameter set and C is the class level. So when C equal 1, this means we have the target. If C is 0, it denotes the class of the noise. And here we assume that the probability of having each class is the same, and it is binary, so it's 1/2. Okay, now we can say the X tilde is from the probability of X when C equals 0, and also we have theta, and we denote this as QX tilde. I wrote as this, like the posterior. This should be tractable to evaluate, or our objective is the logit of the sample U. We're gonna get this logit of sample U, not from the noise distribution, but from the target distribution. So we can write this as the logit of U is log P theta U over QU, and this is equal log P theta U minus log QU, right? And this term is, let's write this as P model, and let's write this as P noise. Step by step. So as I wrote here, the P model can be also written as the X conditioned on C equal 1, and the P noise can be written as the X conditioned on C equals 0. So we can think the C as the switch, which determines whether we will get this X variable from model distribution or from the noise distribution, right? And we want to fit the probability and the probability of P train. Then we can write this standard maximum likelihood learning to fit this probability. So the setter that we want to get is R max of expectation, where we have X and C variable. These are from P train. And the sampled X and C is used to this equation, log P C conditioned on X, right? Now let's think this equation as logistic regression. If you want to detect the class of the target correctly, we want to model this equation. If we were given x and we want to know the probability of the class is equal to the target. And this one, we can rewrite this as p, the joint probability over px. And this one can be represented as p x and c0, the joint probability, plus p x and c equal 1, because this is the binary. And here's px c equal 1. Then we can change it to the conditional probability, since the p c equal 1 is equal to p c equal 0. So to write this in equation, pxc equal 0 over pc equal 0 plus pxc equal 1 over pc equal 1. And we have pxc equal 1 over pc equal 1. So again, this is because we have the same probability of the class distribution, like this. So now we will write this in the conditional probability form. Then we can finally write it as p x conditioned on c equal 1 over p x conditioned on c equal 0 plus p x conditioned on c equal 1. And this is p noise x plus p model x. Here we can write p model x, right? So we can write this probability into this form. Okay, so we were on the way to write the logistic regression equation. So we will use this form. So again, just the same one, and we will get this result. P noise x plus p model x, p model x. Then we will divide form. So we'll write exponential here and then log, so the quantity is the same. And here we have p model x and p noise x. And we still have 1 over here. And this we can write this as sigmoid minus log p model x p noise x. To write it more clearly, this is sigmoid of log p model x minus log p noise x. And this is the sigmoid of logit of u. And this equation is just the sigmoid form of this equation, right? And from this equation, we can now get NCE loss by applying the cross entropy. So let's consider the cross entropy for the binary, and the cross entropy minus the summation of ci log pi. Actually, I'm gonna go through the meaning of the cross entropy later. In this, we can write c1 log p1 plus c2 log p2. And since the probability of c1 and c2 are same, which is 1 over 2, so we can write it as minus 1 over 2 and log c1 conditioned on x plus log 1 minus pc equal 1 conditioned on x, since it is binary. And if we extend to the n class, which is the general case, we can write this noise contrastive estimation loss as 1 over n, and we have summation here, log sigma logit of xi plus log 1 minus sigma logit of xi tilde. So here we derive the noise contrastive estimation loss. An infoNCE is affected by NCE loss, and it uses a category called cross entropy loss. So here we assume that the positive sample is from x conditioned on c, and the negative sample is just from px, the distribution of data, and this is independent from the c. And we can write this as the entire case, and here's the case of positive semantically, and we can refer to this equation again. Okay, let me like this, and you can think that we can write this equation as the summation of pxj conditioned on z and multiply psi px positive, and here right? So in this case, as you can see, we only assume we have one positive sample. And we can write this equation as summation is the same in pxj conditioned on C. And since this, we can write this as just px over pxj, because we think that px is just the factorial of the each xi. So we can multiply like this. So we can write this I is not equal to j like this. And also we can write here px positive conditioned on C and px over px plus positive. Now we can cancel out this term, and we can write this as like this, where the f is the square function, and here fx comma c is proportional to the px here and px conditioned on C, right? So this one we can see is here and also here. So based on this, the infoNCE loss is minus expectation of log probability minus expectation and log of the square function of x positive and C divided by the summation of all the x in our data and fx prime and C. And now to derive the common L2 normalized contrastive loss form, we will see more about this form. So px conditioned on C over px. This equation represents how much more likely x is under context C compared to its marginal probability here. And this form is, so this ratio is a key to distinguish positive pairs from negative pairs. And in machine learning, it is common approach in energy-based model that this ratio is often considered as a log linear model. Okay, this means that we can write this as px conditioned on C over px can be written as exponential of g, which gets x and c, where gx comma c is an energy function that captures interaction between x and c. Okay, so we can model this gx comma c as a dot product of their embedding. So we can write it as if we say this f is an encoder which maps the real observation to the representation vector, we can finally write px condition C over px is equal to exponential fx transpose and fc here over tau, where the tau is the temperature. We started from the categorical cross-entropy loss, but if we loosen the definition of class, we can consider this context C can be the arbitrary data x, and we're gonna have the expectation with respect to this arbitrary data x. Okay, then now we can write this L contrastive loss is minus expectation, and like here we can still see that we have log here. And since we define this square function like this expectation equation, you can write summation of any x in our data large X and exponential fx prime transpose fx over tau and exponential fx positive transpose fx over tau, like this, because we have x positive here and x prime here. So like this and this. Now, let's consider L2 normalized feature vector. Okay, we are almost there. And then let's do L2 normalized feature vector. First, we have two assumptions on the unit hypersphere. The first assumption is about symmetry. For all x and x tilde, where the x tilde is the positive pair, x and x tilde is a positive pair, we assume that from the positive probability, p pos x and x tilde is equal to p pos x tilde and x. Okay, so this is the symmetry assumption. And the second assumption is matching marginal. This one is for all x, integral of p pos x in x tilde with the x tilde is equal to p theta x. So this is the assumption of matching marginal. If you assume this, we finally can get our equation L, contrastive, F the encoder, and when tau and m, the number of negative sample is given, we use the expectation and we assume that x and x tilde, the positive pair came from p pos, and the negative samples x minus I, where I starts from 1 to m, is IID, and this is from p theta. And we can write here minus log. Since we separate the negative samples here, the equation is like expectation fx transpose fx tilde over tau, and we have exponential fx transpose fx tilde over tau plus summation from I equal 1 to m exponential fx transpose fxi over tau. So this is finally the commonly used contrastive loss form for L2 normalized representation. So this is actually end of the derivation, but let's see more about the square function fx, c that we saw before, which is defined as px conditioned on c over px. This is actually related to the mutual information maximization. And the definition of mutual information is if x given y, this is defined as KL divergency of px comma y and px multiplied by py. So the mutual information maximization measure the similarity of the joint distribution px comma y and the multiplication of each marginal distribution. And to see this equation, we have to know what is KL divergency. And let's start from the entropy. So what is entropy? Entropy is the expectation of minimum resource that we need to represent a certain representation. To minimize this amount of resource, we have to transcribe the most frequent information into the shorter form, right? So if you have a plot like this, where pi is a probability of appearance, which is in a range of 0 and 1, right? And let's say the y-axis is the amount of resource. And here the axis is pi. Then we can use minus log function to calculate entropy. So here we can write this as log pi. And we say we are gonna use the expectation. So the entropy is summation of pi, so like an arbitrary point, and the value here. So log 1 over pi, because here's minus here. And what is cross entropy now? For cross entropy, for a certain probability variable pi, the resource is not following minus log pi, but rather than that, this follows an arbitrary distribution qi. So this became minus log qi. This is called cross entropy, so we write this h p comma q as minus summation pi, and we have log qi, maybe minus here. Then finally, what is KL divergency? KL divergency is
KL divergency. If we have a probability distribution P, and we have the approximation distribution Q, and we evaluate how the entropy and cross entropy is different. Of course, entropy HP is smaller or equal to HP comma Q, since Q is just the approximation. So KL divergency can be written as HP comma Q minus HP. And according to the definition above here, you can write this as summation of Pi log Qi in denominator and Pi in numerator. So this is the definition of the KL divergency. And I said before, the mutual information's definition is that x and I for x and y, and it is defined as KL divergency Pxy and Pxpy. And by using this equation, we can write this as summation of y in large y and summation of x in large x. And we have Px comma y here, and log. We have the joint probability distribution in the numerator and Pxpy in denominator. We can see that if x is independent to y, log 1/1 is 0, so mutual information 0. It means that if you have larger mutual information, the two variables are dependent. Let's go back to the square function fx comma c, and let's see mutual information with respect to x and c. So this is some summation and px comma c, and we have log px condition c over px, and we have seen this part. This part is actually the square function of x comma c. So this is why the infoNCE is related to the mutual information maximization. This is end of this video. Thank you.